Welcome to Analog Microelectronic Circuits class. This is lecture 8 on unit 2 and we are discussing on bipolar junction transistors. So in the previous 7 lectures, we looked at the structure, the operation of BJT. We looked at DC related stuff and then we have understood the small signal equivalent circuit. And the previous class, we made an attempt to find the input and output impedance of transistor configurations. So to quickly see what we have done in the previous class, yes, we have done something on input and output impedance from the small signal model in active region, and we have arrived at some rapid simplification methods where looking into the base terminal will give you a resistance of R pi. So whenever we write R pi, it is understood that R pi is actually RE into beta plus 1. Right. Now looking at the looking at the base, it is R pi. Looking at collector, it is R naught, and looking at emitter, it is 1 by GM. I asked you guys to find for these two topologies. I hope you have obtained some result for this. So if some of you got a result for this, can you give the responses in the chat box? If you evaluated the impedance between the terminals collector and emitter with base shorted to collector, if you got some output, some result for this, you can just put the response, put your answer in the chat box. And similarly for the last one, probably this one I will do it in today's class also, because it will take three more additional steps to arrive at the final answer. But everything, if you observe, everything can be done in relation with what we have done for MOSFET, right? So what we will do in today's class is we will definitely will analyze these two things, especially this we will do in today's class. And we also will look at the intrinsic gain of a BJT, and we'll introduce the first amplifier topology, which is common emitter topology, right? So let me start with the intrinsic gain of a BJT. Intrinsic gain of BJT. So before defining the intrinsic gain of BJT, I would like to hear from you guys. Okay, so Kishan, are you there? Kishan?
Yes, sir.
Yes, Kishan. So Kishan, can you recollect what we learned about intrinsic gain of a MOSFET? What was intrinsic gain?
GM or not, sir.
Yeah, so GMR0 is a formula for intrinsic gain. So what does
Yeah,
it signify?
maximum gain
That is available from a single MOSFET, right?
single mode.
Very good question. Yeah. So similarly, thank you, Kishan. Now, similarly, for a BJT also, actually we can understand or we can find the maximum gain available from a single BJT. So we'll take the same approach as what we have done for a MOSFET. This is a single BJT. Assuming that input is given to the base, now we have extracted or we have done the intrinsic gain for a MOSFET by loading it with an ideal current source, stating that whenever you load with a resistance there, definitely that resistance will limit your gain. Now if I bias or if I load it with an ideal current source will offer you an infinite resistance. So I can actually write the intrinsic gain of this BJT. So okay, so I will directly define what is this intrinsic gain here, and let us derive what is intrinsic gain soon after doing common emitter amplifier configuration, right? So can one of you tell me what will be intrinsic gain for BJT also in this case? Can I get an answer from Kaushik Aryan? Kaushik, are you there?
Yes, sir, I'm here.
Yeah, Kaushik. So what will be AV or intrinsic gain? Intrinsic gain is also denoted by AV, which is V out by V in. So as we learn the small signal model of a BJT, can you identify what will be AV in this case? We will do the derivation very shortly. Now, without deriving it, can you tell me what will be AV? Kaushik?
So give me 1 second.
Yeah. All right. Okay. Kaushik, yeah, you can think over it. I'll just give the answer here. Uh, So it is minus Gm into R0. We'll derive it very shortly. Minus Gm into R0, the same form, same intrinsic gain of MOSFET, right? So this is called as intrinsic gain. But now the difference is in the parameters Gm and R0. So what is Gm? What is this Gm? How will you evaluate Gm? Lokita, are you there, Lokita? Lokita, are you there? All right, so Lokita is not there. So your GM is basically IC by VT and R naught is VA by IC, right? So these things we have looked at these parameters, small signal parameters. So that means your AV is equal to VA by VT, or if you write the magnitude, if you write the magnitude of uh, intrinsic gain is VA by VT. Now, if you compare this with the intrinsic gain of a MOSFET, we will definitely recollect for a MOSFET, it was MOSFET intrinsic gain AV was 2 VA by VOV. Right, it is GM R naught, but GM for a MOSFET is 2 ID by VOV and R naught is VA by ID. So your MOSFET intrinsic gain is 2 VA by VOV. But anyway, we will see very shortly how this voltage gain is minus GM into R naught just by plugging in the small signal model over there, right? So that is, so this is the intrinsic gain. So we will look at this the calculation of output impedance of this configuration, because we may use that further. So I have a BJT where a resistance is connected to emitter and I'm calling it as RE, and I am interested to know what is the impedance seen from the collector R out. I will also assume that VA is VA to be considered. I need to consider VA, right? So consider VA, including VA in the sense I have to incorporate early effect also, right? So we know how to evaluate output impedance. Whenever you are evaluating output impedance, what do you have to do is you have to nullify the effect of all the other independent sources. So I have to short V in. So V in should be connected to ground. Then here I should connect a test voltage, which is Vx. That will give a current of Ix. This is the regular procedure. The same thing I'll do here. But before that, let me draw the equivalent circuit of MOSFET. So equivalent circuit of MOSFET is we'll have an R pi which sustains a voltage of V pi, which is connected to the base. Now this is the emitter terminal, and at collector I have a controlled current source which is equal to Gm V pi. Now including R naught, I need to I need to keep R naught in this way, and this is collector and this is emitter. So this is the equivalent circuit of BJT including R naught. Now what I have to do is I have to modify this equivalent circuit according to the diagram what is there on the left. Now base to be shorted to ground because base will be connected to an input, but to find output impedance we need to short it. So that is done. Now to emitter I have to connect a resistance whose value is Re, and to collector I need to connect a test voltage. So I call it as V test, which is providing a current of I test, right? Now I don't know how many of you have tried this V test by I test. If you have tried, you can put your answers in the chat box. If not, I'll do that now. Maybe you can follow the result what I'm getting. Now, in order to start the small signal analysis of calculation of output impedance, the very first thing what I will do is I will look for this V pi. So what I need to do here is I need to get an expression called as V test by I test. Right, that means all the other currents in the circuit and all the other voltages in the circuit should be replaced or should be written in terms of Vtest, right? Then only I can actually write what is this Vtest by Itest. Otherwise, I'll be leaving V pi or some other GM V pi. If I am leaving V pi as it is, then GM V pi also will be there. So that will not actually help in finding the output impedance. So the very first thing what I will do for this analysis is I'll write what is V pi. I'll write what is V pi. Can I get an answer from Kriti? Kriti, are you here, Kriti? Hello, Kriti. Okay, Mohan. Mohan. Okay, Manjunath.
Yes, sir.
Yes. So, Manjunath, my question is, I hope you are following what I'm trying to do here. I'm trying to find the output impedance.
Yes,
Right. Now,
yes,
how
sir.
will you write V pi?
Sir, it's RB, sorry, IB into R pi.
IB into R pi. Okay.
Uh,
Yeah, but if you look at this source, if you look at the circuit diagram, the only source is Itest. Itest is the only source.
yes, sir.
Right. Now, Itest current is coming here, and maybe we can say that some current is flowing through R0 and GM Pi is actually flowing through the other side. So, what is the current through R0?
Sir, I test by GM.
No,
Sorry,
Itest minus
actually, I
GM.
was saying V pi, sir. V pi equals to I test by GM. I mean,
Itest by GM. Okay. How can I say that?
sir, actually, I took I test is equal to GM V pi.
Oh,
So,
Itest is not GM Pi, right? Itest is a sum of GM Pi and the current which is flowing through
oh,
R0.
yes, sir. Yes, sir.
Okay, yeah, I'll help you. I'll help you, Manjunath. So what you can see here is, you can see that this R pi and Re both are in parallel,
Yes, sir.
right? If both are in parallel, both will sustain the same voltage.
Yes, sir.
So if the voltage across R pi is V pi, then in this case, since R pi and Re are in parallel, both will have
Yes,
a V pi voltage across it.
yes, sir.
Now, I test is a current which is originating here, which is splitting into two branches, and what is coming out?
I test.
It should be I test. So how can I write V pi?
I test into RE.
I test into R pi parallel to Re because both are in parallel,
Yes, yes, sir.
right? But there is one difference. Current is flowing through like this into R pi and Re, but we marked V pi as plus minus in this form.
Yes,
So,
sir. So
so I
it's
need to actually
minus,
put a minus sign. Very
minus.
good,
Yes, sir.
very good, Manjunath. Yes, thank you. So your V pi is minus I test into Re parallel R pi. Now let V pi, let it be there. So what I can do is throughout this calculation I can replace V pi with this expression so that your final expression will be without any V pi component in that. Now let me write what is current through R naught. So I have written it before. Current through R naught is the total current is I test. From I test, GM V pi is a current through other branch. So R naught is carrying a current of I test minus GM V pi, right? If that is the case, voltage across R naught can be written as, what is voltage across R naught? Voltage across R naught can be written as this current, which is I test minus GM V pi into R naught. Right. Now, the ultimate aim is to find what is V test by I test. Now, look at the circuit diagram. You can see that V test is connected from this point to ground, right? So, if I want to write what is V test, if I can write the drop across R naught and drop across Re, where R pi and Re are in parallel. So that is in turn it is equal to V test, right? because V test is from this point to ground, from this point to here you have R naught, and from here you have RE parallel to R pi. So if I can write the drop across R naught and RE parallel R pi, that is equal to V test itself. Right. So can I write V test as, V test can be written as the current through R naught, which is I test minus GM V pi into R naught, that is a drop across R naught, plus I test into R pi parallel RE, right. So V test is I test minus GM V pi into R naught plus I test into R pi parallel RE. If this is the case, so this is equal to V test. So any clarification required in this?
Excuse me, sir.
Yes.
Sir, will you explain that equation once again, sir?
Which
V-test
equation, Praveen? V test. Yeah, I'll do that. I'll do that. Yes. Yeah, I think Kirtana, you are writing the final answer. Yes, I think yeah, you got the correct answer. Now, yes, Praveen. So look at this. I want to write what is V test. V test is the voltage from this point to ground. So I can write V test is equal to the voltage across R naught and the voltage across RE. Is that clear, Praveen?
Yes, sir.
Is it clear?
Yes, sir.
So voltage across this resistance plus voltage across this resistance. The sum of these two will give you what is V test.
Yes, I got it.
All right. Now now it's very simple. What you can do is you can just write what is V test by plugging in what is V pi into this. Now if I do that, I can write it as I test. V pi is minus, so it is plus GM into I test into, I am just substituting everything together, R pi parallel to RE. Now I need to multiply one R naught here and one R naught here, plus I test into R pi parallel to RE. Now if you can take common the stuff, so V test is equal to I test, I can take common. What is left out in first term is R naught. Second term is GM R naught into R pi parallel to RE, and third term is R pi parallel to RE. Right. So this is what we have. I hope this is clear. So from this I can write what is V test by I test. So let me take this to next page where I can. So this is V test by I test, which is equal to say if I am taking yeah, I'll take this as R naught, and yeah, there are three terms over there. So it is R naught plus GM R naught into R pi parallel RE plus R pi parallel RE. These are the three terms: R naught plus GM R naught into RE parallel R pi plus RE parallel R pi. Right. So this can be further written as if I take R naught in common, I can write this as okay. So I can take this GM R naught plus 1 into R pi parallel RE. I hope this is clear. So I have just taken R pi parallel RE common and I have written in this way. And if you remember, we have done some simplification even before in common source with degeneration resistance. GM R naught plus 1. If your GM R naught is a large value, 1 can be neglected. So this can be written as R. So this is approximately equal to R naught plus GM R naught into R pi parallel RE. Right. Or I can write the output impedance. So exact formula, you know what is exact formula. I'm just applying certain approximations here. Now if I take this R naught common, I can write it as 1 plus GM into R pi parallel RE. I have taken R naught common and I have written in this form. So this is an approximation of the output impedance of a transistor, a BJT, with a resistance connected to the emitter. Now the value of R out now largely depends on how your R pi and RE are related. Right. Let me just complete and then I'll explain further. So now depending on, so now the value of R pi and RE will largely contribute. That means if I can take two cases. Now if your RE is very large compared to R pi, if that is the case, what will be R pi parallel RE? The parallel combination will be the smallest value. So since RE is very large, I can write in that case your R out will be approximately equal to R naught into 1 plus GM into R pi. Right. R pi parallel RE will be equal to R pi if R pi is small. Right. Now what is GM into R pi? So how can I write GM into R pi? If you remember, GM is actually IC by VT. What is R pi? R pi is VT by IB. Right. So what is GM R pi? GM R pi is IC by IB, which is equal to beta. Yes, very good, Kirtana. Yes, it is beta. So this can be approximated as R naught into 1 plus GM R pi, which is approximately equal to beta. So your R out is approximately equal to beta R naught if your the degeneration, if the resistance connected to the emitter is very, very large. That is case 1. So this is case 1. Now I can take another case as case 2 when your RE is less compared to R pi. In that case, I can write the output impedance as approximately equal to R naught into 1 plus GMRE. Right. R naught into 1 plus GMRE. So then this will be the, or it is approximately equal to GM R naught into RE. So this will be approximately equal to GM R naught into RE. So this is the this result is in comparison with the MOSFET what we have seen before, right? Yeah, because in the case of MOSFET, you know that your R pi is if you imagine for a MOSFET, your RE will be definitely very, very small compared to your R pi, because R pi was infinity in the case of MOSFET, because there is no input impedance connected, right? That is why we have ended up in a this result GM R naught RE, which is similar to that of MOSFET. I hope this is clear. This is how you will actually get the output impedance of a transistor when there is a resistance connected to the emitter. Yeah. So any doubts on this? Any doubts? Okay. If you have, you can ask me. Let me just continue this and start BJT by BJT amplifiers. So let me start with bipolar amplifiers. Since most of the approach is same with respect to MOSFET, the only difference is we are using BJT as the active device. That is the only difference. So the differences in the equivalent circuit will be there. Rest everything will look same itself, right? So as similar to MOSFET amplifiers, even BJT amplifiers, we have three cases. One is emitter common. We will give input to base and output from collector. The second thing is probably we can look at this. We'll have an emitter resistance. We call it as degeneration resistance, and we'll take output from collector. There also emitter is common, but through a resistance. All right. Yes, Kirtan, I'll come back to that question at the end of the session. Now, the third is you are giving input to base, taking output from collector, sorry, emitter, keeping collector as common. So when I say common, it is AC ground. That is the third case. And the final case is giving input to emitter, taking output from collector. Your base will be AC ground. Right. So based on this, we will name this as common emitter amplifier. So always the amplifier name is identified by looking at the input and output. So this is common emitter amplifier. Sorry. This is C amplifier with the degeneration resistance. Now this is common collector, and this is C common base. Right, these are the amplifier topologies. So what we'll do is today we will look at common emitter amplifier and derive the various parameters like input impedance, output impedance, voltage gain, and in BJT amplifiers there is one more parameter which is called as current gain. So let me start with common emitter amplifier. Common emitter amplifier. So taken the active device, input taken the active device, input will be given to base, output will be taken from collector, but I will actually connect a resistance as the load. I call it as RC, and this is VCC. Since the emitter is common, this is common, we call this as common emitter amplifier, right? Now we actually, when we study amplifiers, we have to look at two parts. If you remember, in MOSFET also we have done the same thing. There is something called as DC analysis, because the DC operating point, for example, in the case of MOSFET, it was ID, the drain current, and the voltage VDS and corresponding VGS, right? To ensure that the device is operating in the proper region of operation. Similar to that, in BJT also we have to make sure that operating point is maintained. That is ensured by the help of biasing circuits. So as of now, I will assume that biasing is proper, but later when we take up numericals, I'll bring in the voltage divider biasing and we'll do the discussion based on that. Whether is that fine? Can I get your responses? Are you guys with me? Are you guys with me? Can I get response in the chat box? All right. Okay. So now, yeah. So for just a small announcement in between, those who have come as branch transfer students, you would have informed me. Yes, and I have replied to you back. If you are not feeling comfortable in the discussions what we are doing now, it is only because that you are not familiar with the things what we have done before. So it will take some time. Patiently listen all the previous lectures. I will help you out, but continue listening to the present lectures also. So at some point, yeah, definitely you will get a link and you can connect and you can proceed further, right? So all right. So coming to this common emitter amplifier, what I would ask you is to find the voltage gain, evaluate the voltage gain of this circuit. Maybe you can neglect R0 for a while. All right, Subramanian, yes. Yeah, I'm asking all of you to find the voltage gain of this common emitter amplifier. So what you can do is you can replace the BJT using its equivalent circuit, and then you can find voltage gain expression, right? So while you guys trying, let me check with few of you. Anushka, are you there?
Yes, sir.
Yes, Anushka. Anushka, are you following what we are doing now?
Not completely, sir, but like I should revise once more, and I should sit and try it again, sir.
All right. So you try it now and let me know where you have a difficulty.
Yes, sir.
Yeah. Irshad?
Yes, sir.
Yes, Irshad. So are you getting answer for this voltage gain? How will you do that?
Wait.
So what should be done first? What is the first step? Irshad, are you there? It's all right if you're not. I can help you out. That is why I am just calling names. Hello, Irshad.
Yes, sir.
Yeah, Irshad. Tell me.
So, what is scientific to follow?
So you
Not
have a
getting it, sir.
you have a circuit with you right now.
Yes, sir.
Yeah. What I want to find is voltage gain. So what is voltage gain?
Voltage gain is output.
Output.
Um,
All right, Irshad. Yeah. Please go through the lectures and make sure that you are following classes, right? If you have difficulty, we can definitely discuss it. So voltage gain is nothing but V out by V in. So if I want to find, so let me just tell this again and again. Voltage gain, what we are finding is how this circuit will respond to a small signal, right? How we can say, for example, you have an audio signal, how to amplify that audio signal. Now your audio signal is in the range of milli or microvolt. That is why that means the input coming to the circuit is a very small signal. That is why we are replacing transistor using its small signal equivalent, right? So why are we replacing transistor using its small signal equivalent? Because we know that the input to the transistor is a small signal. Now since input is small signal, if I want to study about this circuit in the presence of an input signal which is very small, I should replace transistor using its equivalent circuit, and that equivalent should be what? That equivalent should be small signal equivalent. So since I know the small signal equivalent, I will just draw it here. The small signal equivalent is on input side I have R pi, which sustains a voltage V pi. Now on output side there is a dependent current source which is GMV pi. So this is the equivalent. I can include R naught also. Since we are doing amplifier circuit, let us do step by step. Let us do first without R naught and later we will include R naught. That will be easy. Now this is your base terminal, collector and emitter. Now, so the first step is replace transistor using its equivalent, appropriate equivalent. Yes, Karthik. Yeah, there is a small clarification there, Karthik. Probably you will find it now. Yeah. Now this is your equivalent. Now I have to modify the circuit. So while modifying, emitter should be grounded. To the base, I have to connect the input signal, which is V in. To the collector, there I have to add a resistance RC, which is connected to ground, and this is V out point. Right. So what I want to do here is I want to find the gain of the circuit. So before writing gain, let me write what is V in. What is V in? V in is connected between base and emitter. That is, in fact, the V in voltage is coming across R pi, or V in is equal to V pi. That is the first step. Now the second step is I'll write what is V out. What is V out? V out is a voltage across RC, but there is a current flowing through RC which is in the opposite direction, which is actually creating a voltage like this. So I will write V out as minus GM V pi into RC, right? Or I can modify this and write as V out equal to minus GM into V in into RC, or V out by V in, which is called as voltage gain, can be written as minus GM into RC, right? This is the voltage gain of this circuit. So let me, so while try to understand this, what I have done. Meanwhile, I'll just take the MOSFET circuit so that we can have a comparison. Yeah, I hope you can see the MOSFET circuit. So here the circuit what we have taken is common source amplifier, there is a resistance RD and there is an input signal, right? Now here the analysis we have done little detail because there we were first time we were introducing a DC source, AC source, so that is why I have taken a lot of steps there. Now I just replaced it with the equivalent and we obtain the voltage gain as minus GMRD, and you can see that the expression remains same. In place of RD you have RC, so it is minus GM into RC, right? So let me just verify the chat box. Yeah, yes, Karthik, I hope Karthik you understood what is the mistake, because yeah, R pi is the voltage across R pi is V pi, which is equal to Vin. So gain means you will not get that term. Right.
Yes, sir. I took RO.
Yeah, very good. Yeah. Oh, you included R naught also. Yes. Okay. Now in this case, so this is voltage gain. Now you know that if you include R naught, okay, let me before that let me just write what is R in. What is input impedance of the circuit? You can do this. So when you find input impedance, you have to connect a test voltage here at the input side, and you have to measure what is V test by I test. It is straightforward. It is directly R pi. So Rn is equal to R pi, and R out is equal to RC. These things I can directly write. If you have doubt, please ask me. I can clarify this. So Rin, the input impedance is R pi, and output impedance is RC itself. Right. Now R pi can be further written as what it is, beta by GM. Those things you can you know, and you can write it better. Right. So this is without early effect. Now if I am considering early effect, now with early effect, the only difference is, let me take this equivalent circuit as it is, and I have to add a component here which is R naught, right? Now emitter is ground, RC is also connected to ground, so the only difference is here AV becomes minus GM into RC parallel to R naught. What about input impedance? There is no change, which is R pi. Output impedance, there is a change, which is RC parallel to R naught. Right. So apart from all these things, one more additional parameter what we look in circuits, especially common emitter circuits, is something called as current gain. We call it as AI, which is called as current gain. So current gain is output current by input current. Output current here is IC. Input current will be IB. IC by IB is nothing but beta. That is why we call beta as common emitter current gain. Right. So what we have done is I have just taken a common emitter topology and analyzed it using small signal analysis to obtain the voltage gain, input impedance, output impedance, and current gain in presence of R naught and without R naught. Right. Now probably I think you can go back and you can tell me how to arrive at the intrinsic gain of a BJT. So how will we do that? Yeah, so what I need to do is I need to replace this using, this is GM V pi with an R naught. On input side we have R pi. So this is ground. To the input side I need to connect V in. Output you have a current source. Current source is a DC current source. The resistance across current source is infinity. If that is the case, that can be replaced using an open circuit. So no need to connect anything. You have the current source resistance open, which is in parallel to R naught. Right. So V in is equal to V pi. So your V out is equal to minus GM V pi into R naught, or your V out by V in is equal to minus GMR, which is the intrinsic gain of the BJT. All right. I hope you guys understood what I have done for intrinsic gain and for yeah, intrinsic gain, and then this analysis, and finally the common emitter topology. Right. So if there are doubts, I can discuss it right now. So what I'll do is I'll be winding up for today's class. So what we have done today is we have we analyzed the intrinsic gain of a BJT common emitter topology, and also we have analyzed the output resistance of a BJT when there is an emitter resistance. So we'll continue this in the next class. Next class we'll look at more the other topologies, common base, common collector, and common emitter with degen, and then we will come back to the numericals and we'll thoroughly look at biasing as well as the small signal calculations. So thank you for joining. Hold on, let me